You ready, mate?
Yep.
Okay. Cool. All right, so let's get started. So, I think a lot of you were here last week, right? Or most of you were? Were you here last week? That's fine. So basically, just to quickly summarize, right? What we're doing is we're doing a series of workshops on different topics for coding interviews. Basically, we're going through just like a list of things. So we started with arrays last week and hash maps. So today we're doing trees. Maybe next time we might do some like more like advanced graphs. And then just kind of go around different topics. It's good to kind of get a good overview, but it's just more of like an introduction to like tree type questions. So today will be a little bit more hands-on than last time, since last time was more of an intro. Today we're going to be doing lots more problems, and we're going to be really just delving deep into tree problems. So we already did this spiel, but we're going to be doing basically LeetCode. And specifically, we're going to be working on trees. Today we'll do binary trees, but I can also quickly explain other trees as well. So raise your hand if you don't know what a tree is yet. Okay, so you all like have some idea of a tree, right? It could be either like discrete structures or data structures. Alright, raise your hand if you know what a tree is, but you haven't solved any problems yet with trees. Alright, you guys know? Okay, that's good. It's good. This is exactly for you. Because basically, when they teach you data structures in Queens, it's a very like theoretical idea. They kind of teach you the theory of it, they don't really teach you the applications of it. Like they'll teach you about like heat, but they'll never teach you like when to use the heat. Or like they'll teach you what a graph is, but can you solve graph problems? Probably not. So it's a very, at least for my professor, it's very, very heavy. So we're going to be focusing on the actual practical applications of it. So just to kind of give you all a bit of a overview on trees, it'll be very quick, right? We know trees have two properties, right? Or I guess three properties. They have a value, and they have a left for a binary tree, and they have a right. Right? So, for example, here's a tree node, and say it has the number 5 in it as a value. It's going to have a pointer left and a pointer right, which will point to other tree nodes, which is optional. So you can have nothing. It can be pointing to nothing. So in Python, there's something like this. Class node, right? And it's going to have a, and say like you take in a value, right? You're going to do something like value is equal to whatever value you give it, and then left is equal to none at first, or null, and then right is equal to null or none. So that's kind of like the basic class of a tree. Just so you know, right? So here is a tree, and it has a left child of 2 and a right child of 3, and then we can always just keep going on. Left child of 1, left and right child of 5 again, generic tree, and say this one has a left child of 7. Right? This is a tree. Very basic data structure. We have a value, and there's left and right. It looks like this, but in code it will look like this. Alright, are we all in agreement of what a tree is? Cool. Alright, so the most important thing that you can know about trees is just how to traverse them. Specifically, there are 2 different types of traversal, depth first search and breadth first search. So we're going to be focusing on that today. In general, trees are recursive, right? Because where each node has a left, right, up, and other nodes, so it's just like a recursive structure. So depth first search is a lot easier to do with this. So basically, we're going to go over 3 different versions of depth first search. Pre-order, in-order, and post-order, and then we're going to do those on LeetCode, solve some problems, and then also do some breadth first search as well. Great. So depth first search, that's the most important algorithm for any coding interview. If you do like the blind 75 list for coding interviews, I think like 21% of the questions can be solved with depth first search. Because you can do backtracking with depth first search, you can do graphs with depth first search, you can do trees with depth first search, you can do dynamic programming with depth first search. So depth first search is super, super important, and trees are a very easy way of getting into it. So the way depth first search works is kind of in the name. You go depth first. You go as far as you can in one direction before moving back. So what that means is, let's say we're doing a specific traversal. I'm not going to say which one, but I'm going to start with a traversal. So we're starting from 5, and I'm going to go all the way down as far as I can, and we see that at this point there's no more nodes, so this is called a leaf node. Right? If a node has no children, it's a leaf node. Again, it's just a root in case it's to be reviewed, but you know, root, no children is a leaf. So we found one, we search it, Alright? And now we're going to go back. We found 2. Alright, and we're going to go here. We found 5. And at this point, we've searched the entire left subtree. Alright, let's go to the right subtree. The first one we found is 7, 7, and then we can go up. Right? And then we found 3. Alright? So this is a specific vector search called in-order traversal. The way it works is you go as far as you can, basically search the left subtree recursively, go as far as you can until you reach a leaf node, and then search its parent, and then search for the right subtree. Any question? You have a question?
There's 2 5s, so are you
I know.
also,
But this is a generic tree.
oh, okay.
A generic tree can mean anything. That's a good point, and we'll talk about binary search trees next. So this is called in order. Why this in order is an important aspect, actually, let me fix that for you and show you why. So let me actually change the order, the name of these things to represent a binary search tree. I should have actually probably done that in the beginning. So let's say this is 8. Let's say this is 5. Let's say this is 3. Let's say this is 7. Let's say this is 10. Let's say this is 9. Alright, this is a binary search tree. Why is this a binary search tree now? Yeah. Exactly. So, yeah, good point. VSTs, the property, right, is for each node. For each node, left is less than current node, which is less than right. Basically, the left node of each node is going to be less than the current node, and the right node of each node will be greater than the current node. So here, 8, for every node, it's going to be less, right? So 5 is less than 8. And for every node on the right of 8, it's going to be greater. So here is 10, 10 is greater than 8, so this is valid. From here, 5, 3 is less than 5, which is valid. And 7 is greater than 5, which is less than 8, which is valid. Right? And then here, 9 is less than 10, which is valid. Okay, this is a binary search tree. So the order that we just did, in order traversal, and I should have started with that actually. So we'll start again, right? In order, we start all the way left first to the leftmost node. That's going to be 3, right? So once we hit the leftmost node, we add its parent, which is 5. Then we go to the rightmost node, which is 7. And so we've done the left subtree. So now we go here to the parent, 8. And then let's do the right subtree, which would be 9 and 10. So what is special about this property that we just did? It's in order. It's specifically, it's what? It's ascending order. It's a sorted list. Yeah. So this is sorted. So that's a piece of really important trick. Right? If you're getting binary search tree problems, in order traversal is going to give you sorted order. And all you have to do is like if you have like a DFS function or something, right, that takes in like a root. Right? What's our base case while we're searching? Not exactly. Even further than that. If we hit null. If at any point we're done, like we've reached outside of bounds, we're done. That's our base case. So like our base case is like if, in Python we say this, if not root. So you could, or you could say if root is equal to null, or whatever. If not root, return. Right? So basically, once we reach outside of the tree, we return. Next step, what's our recursive case? So we want to do left subtree first, then process the node, and then right subtree for in order. So that would just be DFS root.left, and then process the node, which could be whatever. You can print it, you can do whatever, and then DFS root.right. And that's the entire code. That's the entirety of in-order traversal. It's like 4 lines, right? So basically, we're just saying, okay, did we hit a null pointer, or else we're going to recursively search the left. So let's start here. We're at 8. Is this our base case? No. So we're going to search left. We're at 5. Is that our base case? No, we're going to search left. Is 3 a null? No. Is that a base case? No, so we're going to search left. At this point, we've reached null, right? So we're going to return here. So now we're here. We're going to process 3, which we added over here. Then we're going to go to the right subtree. There's nothing there. We return here, and then we return here. Same process. We process 5, and we go to the right. Does all kind of make sense? It's good to draw it out and see the steps one by one, but it really is that simple for DFS in order. Pre-order traversal is where you go for the parent first, then the left, and then the right. So all you have to do is swap these two lines of code. If you process the node first and then do DFS left and right, that'll work. So if you do it over here, 8 would be processed first, with DFS left. 5 would be processed, DFS left. 3 would be processed, right? DFS right. So as we go on so far. Right? And if you want to do post order, you swap these two. So these two lines of code. And that's it. That's the entirety of DFS. Where post order is that you do the children first. So 3 and 7 we searched, right? And then it would be 5, and then it would be 9, 10. Right? So it's good. It's all you are moving is one line of code, or whatever you're doing to process the node. Any questions so far on like DFS? No? Okay. So that's DFS. I feel like this is the easy algorithm because it's recursive and it's legitimately 1, 2, 3, 4, 5 lines of code. So hopefully you can memorize 5 lines of code. Things could change because obviously this process node can mean many different things. It could mean do lots of different things to it, so it could add more lines of code. But in general, this is like the template. Alright, let's do a different search. So we've done DFS, and we've done 3 versions of it. In order, pre-order, post order. Right? Any questions before I move on to the first search? No? Okay, cool. So then we're going to just do one more. So again, DFS, very simple, follow the code. You're just going as far as you can in one direction, processing the node, going to the other direction, or do it in any order that you want to make pre, post, or in order, depending on the question. If you get a LeetCode question, for example, in my Google screening interview, they asked me, like, given a binary tree, delete the children nodes before their parents. So that was my interview question, which is pretty easy. That's just post order. So if I do post order, I delete the children, and then I delete the parents. So that's the entire engine for that problem. If you get something like a binary search tree asking to do stuff with that, in order is probably your best friend because binary search trees are sorted if you do it in order. So that's something to think about. If you have to deal with the parents first before dealing with the children for some questions, then do pre-order. Either way, it's all about just moving this process node either up or down. That's really all I have to do. Okay, anyways, last chance. Any questions on this? Cool. Alright, so let's move on to the second and the only other search that you need to really know about before we do some actual problems. It's called breadth first search. So depth first search is going as deep as you can into one direction before you move on. Breadth first search is the opposite, which is where you want to go level by level, is what we call it. Level or traversal is a different way of thinking about it. So the way it works is we go here, we go 8, and we're going to process as children first, which is going to be 5 and 10. Right? And then process the children, which is 3, 7, and 9. So I'm literally going level 1, right? That's 8. Level 2, here, level 3. Pretty simple, right? We're just going one level as we go. So if we had more levels, it would just keep going. How do we implement this? We can't do this recursively at this point, so you actually still have to use other data structures to solve this problem. And here's where I'll quickly also touch upon differences between DFS and PFS, because actually we're going to do this iteratively using a data structure, but if you just change one like 4 letters in Python, you can make this into DFS. This is what Python's better than Java. Anyways, the way this works is we have to kind of emulate what we would do with recursion. So with recursion, we're actually using a data structure secretly to do things recursively. Does anyone know what data structure we're using in recursion specifically, like under the hood? The stacks. Yeah, you should either know this by now, or you should definitely know it because it's really important. Recursion uses a stack. It's called the call stack. So whenever you're calling recursive functions, it automatically goes on the call stack, and it'll automatically pop it from the call stack as you keep going. If you need some more information on that, there's a video on YouTube from Harvard CS50 that talks about recursion and the call stack, and I recommend you watch that. But anyways, DFS uses a stack under the hood. So if we had gone through this, right, and say let's do this one by one with DFS first. So we're gonna add 8 to our stack, right? We're gonna add 5 to our stack, and then we're going to 5 and 10. We're gonna add the children. So 5, 10, say 3, 7, 9, right? If you pop from the stack, go from 9, so 9 is our first finished actual process node. Then you go to 7, 7, which is the right node, and blah blah blah. For BFS, we're going to use a queue. So what we're going to do is we're going to go for each level, for each node, add its children to a queue. So here's a queue. We're going to add 8. Okay, so for each node, we're going to start with 8. Let's go from there. All right. While the queue exists, we're going to pop the nodes. So our current is going to be the left. So in Python, we use pop left. Right, so now we have 8. So at this point, 8 is our current, okay? We're pointing here. We're going to add children to queue, right? So here's our queue. 5, 10. Okay? And then somewhere in here, sorry, I forgot to add process to the node. So what does that mean? It could be anything. So let's say we want to just print it out. So at this point, we process a node, we've gone to 8, right? So now we're going to add the children to the queue, which is 5 and 10. And then at this point, that's the entire code. We're going to repeat over. While the queue exists, pop left. So that's 5. So now we're at 5. We're going to add this, we're going to process that node, so we're going to print it out here. 8, 5. Add its children to the queue, which is 3 and 7. Okay? And move on. All right, next step, we're going to pop left again. 10. We pop 10. So now we're adding it to the nodes. We're going to add its children, 9. So 3, 7, 9. That's our queue. Right? At this point, if you notice, we finished the second line. All right, let's keep going. Pop left. We got 3. Does 3 have any children? No, but we're going to process it, add it to our list. We got that so far. 7. We're going to process that. Right, pop left from our queue. There's no children, so we can't add anything to our queue. 9. Any children? No, we pop left. We add it to our output, and we don't have children, so we can't add any more to the queue. At this point, this while queue condition is complete. There's no more queue. We exit our while loop, and we're done. We've done level by level traversal. Right? And that's the breadth first search in a nutshell. There are some times where you might want to actually care about, like, are we doing this level by level? Because right now I didn't really track how many levels we've done. We've just kind of been processing the nodes. So if you are trying to track that, let me show you kind of how that would work. So we just add a for loop. So it'd be for whatever in range length of queue. By doing that, again, just curve, right, to left, top left, whatever, process, and then add children. By doing this, if we can say something like level is equal to 0, after the for loop, level plus equal 1, and then whatever. So the way we're doing this would be something like, all right, let's have 8 as an example, right? We have 8 in our queue, we pop, so that means the length of our queue right now is 1, right? So we're gonna do our stuff, we're gonna add 8, we're gonna process it, whatever. At this point, we're gonna add a children 5, 10. But remember that we checked this before, so right now this is 1, so this for loop is done, so levels equals level 1 now. Then we're gonna add 5, 10, we're gonna process those as we go on, and once we've done that, level would not be equal to 2. And that's basically the only difference. But besides that, that's BFS. Any questions on just the conceptual idea? Because we're going to actually code it out in a second. All right, cool. Any questions on either one of those two search algorithms? All Alright, so your homework is to memorize these once we actually write them out, because it is very, 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 very important that you memorize them. That's like the one thing that you need to know is BFS and DFS. So let me just turn this on again, and let's do some LeetCode. Okay. Alright, so first question. Binary tree in-order traversal. So literally we're just going to do DFS on the binary tree. So given the root of the binary tree, return the in-order traversal of this node's value. This is basically what I just said. It's what we just did. So code it up, I'll just quickly show you that, right? So we have in-order traversal. So first we have to create a array for our output, right? So output is equal to an empty array, and then we're going to do a DFS. That DFS we're taking in the root. Base case, if not root, return, and then what's the other stuff we have to do? DFS root.left, output that pen root.value, DFS root.right, and then return output. I'm pretty sure this is the entire code. Wrong answer. Expected. What did I do wrong? Root 1, output 1. What? Check. Yeah, actually, wait. Let's see. Where'd it go? Oh my gosh. Disappeared. Let me refresh the page. Oh, I forgot to call the function. So, yeah, whoopsie. So DFS root, return output. There we go, accepted. I just forgot to call the function. But yeah, that's basically the entire code, right? This is our template. DFS, if not root, return. In order to DFS root.left, output 10, then DFS root.right. Don't forget to call the function. Alright, if it was pre-order, I just literally move this here and do it here. And that's pre-order. If I wanted to do post-order, I literally just Control X, put it here, and now we've done post-order traversal. It's really that easy. It's just moving one line of code. Alright, any questions on this specific in-order traversal? I'll let you guys write it down. Because this is your template, you need to memorize this and be able to literally come up with this in your sleep. There are very few things you actually have to memorize for a Java tree, but this is one of them. You need to know DFS. And in the meantime, yeah, I'll take a picture, whatever. Yes?
That's my question is, how do you know when they
For trees, it's usually, unless they ask you specifically a level by level, or if you care about level, then do DFS, or else I would just default to DFS for trees because it's easier. But for most questions, you can do them with both. So it's really whatever your preference is. Actually, what I recommend is doing it with both. So if they give you like a problem that can be solved either way, do it with DFS and then do it with BFS. So you're practicing both algorithms. That's what I do with all my problems. So I have like 60 lines of code for those LeetCode questions because it's just like I have a DFS, I have a BFS, and I have a DFS iterative using a stack as well just to practice that. It's good to like really understand those at that level. Alright, let's do invert binary tree. We hide our solution. Alright, so invert tree. Let's look at that. Let's look at this question. So given the root of a binary tree, invert the root of the tree and return its root. What does that mean? So we're even given the picture. What's happening in this picture versus this picture? Anyone tell me? Yeah. It doesn't have to necessarily be that, but specifically, what's changing with these two trees? Yeah. Exactly. You're just flipping it over. So the left is equal to the right, and the right is equal to the left. So over here, right, you can see 1 and 3 becomes 3 and 1. And then 6 and 9 becomes 9 and 6. 2 and 7 becomes 7 and 2. And basically everything from this is flipped over to that side, right? Alright, so how can we do this? Does anyone have any ideas?
Maybe we could do this keyword or something, and then we could just like
We could do a queue. We could do BFS on this. But let's try DFS because it is a little easier. But we could follow up with how you use a BFS. But let's try with DFS because that's our. This will make it a median if you do it with DFS. This is an easy. Yeah.
maybe just start on the right side. Like,
You want to do the right side?
yeah, like start on the right side of the keywords, and then go from there.
You could do that. So basically, but what do you mean to go from there?
Oh, from like maybe print.
We're not printing. We're actually physically changing
Oh,
the tree.
okay.
I like to think on it. What's up?
We make the left equals 2 I equal 1, and for the right we make it equals 2I, and then root 2I equals 1.
I like very like if I can speak a little louder.
For the roots we use I over 2,
I over 2.
yeah, to get the parent, the roots, and for the left side we multiply by 2 and add 1.
I think you're thinking of a heap. That's how you. I think that's how you do like the that's the algorithm for creating a heap. That's different. This is a binary tree.
No, I'm saying for binary trees, put it on a tree. The parent is usually multiplied by 2.
Yeah, that's for a heap. You can create a heap, which is a different data structure. It's called a min heap or a max heap. And you portray it like a binary tree, but you use it with an array. You talk about I divided by 2 plus 1, stuff like that. I'm pretty sure you're talking about a heap. But again, Python you have heaps built in, but I think you're talking about heap because there's no division or anything on the top. Yeah.
What about if like we're seeing what matches on the left tile and see that matches on the right tile, and then switch them if they're on the same.
So I'll give you all hints. Yours are similar. What's the easiest case? What's like our easiest? What's our base case? What's like the super easiest thing that you could possibly do? If you can imagine this was like the easiest version of the problem. The most easy version you can pick up. What would it be? What?
Yeah.
What's easier than one node? No nodes. The easiest version is if there's nothing, right? Because at that point you're done. So that's going to be okay. So let's do EFS function taking a root, right? And if not root, return. That's our classic DFS base case, right? Easiest case, just do nothing if there's nothing there. All right. So then, what else can we do? So what's our second easiest case? Say that we have 2 nodes, right? Say we have a parent and 2 nodes, 2 children. What should we do to those parent and 2 children? Traverse? Not traverse. So like say I want to invert 2. So like right now we talked about how we get the left side tree, swap it over like a mirror, get the right side tree, swap it over like that. So what if you only had a tree of 2 and 1 and 3? What's the easiest? What we have to do to mirror this? Yeah, exactly. We just swap the 2 left and right. Right? That's like the second easiest choice. Either you have nothing, which is super easy. That's our base case, or else just swap the left with the right. So we can just do that. Root dot left, root dot right is equal to root dot right, root dot left. That's how you do it in Python. So at this point, we've gotten so far. And then what do we do next? We have to do recursive calls. So just DFS, root dot left, and DFS, root dot right. And then I'm pretty sure that's basically it. Then you say DFS root, return root. And we just comment the old code I had. And if I run this, it's accepted, it works. That's basically the entire code. So what did we do? We did actually pre-order, if we think about it this way. For each parent, we just swap the children. but it's like literally pure traversal. There's nothing different about this. The only thing is instead of printing out the node, we swap the children. So all we're saying is if we hit the base case of nothing being there, we're done. It's easy. Easiest case. Or else swap the two children recursively. So if we're saying form, right, we're just saying swap these two children, and then do the same here. Now we're here, swap these two children, now we're here. The algorithm will still work. Swap two children, which both are null, right? So we're just swapping null with null, so it doesn't really matter. And then we go to the edge cases, basic, which are null, right? And then we move up. And we do the same thing over here, recursively. So all we're doing is, remember, for recursion, base case is usually the easiest case possible, and then your recursive case is just one step easier. So in this case, no matter how big the tree, swap the left with the right, and then recursively do the rest. So that is inverting a binary tree. Does anyone have any questions on this problem? You will all see like how this is basically just pure traversal, except for like one line of code difference. Yeah.
I'm a little confused on the third level, right?
Mm-hmm.
If you flip the 3 and 1,
Mm-hmm.
how does the 6 and 9 flip to the other side?
Because we're doing it recursively. So we're starting from here, right? 4. Then we're saying swap 2 and 7. So now these are swapped, but then these are still unswapped. But let's just say we've done that, right? So then we're going to look at 7, which is here, and we do the same thing, swap 6 and 9. So 6 and 9 are now swapped. 7 is in this position. And then you go to the right side next, which would be 2, and swap the children, which is 1 and 3. We're going to want to swap those. So it's recursive. That's the thing that's kind of hard to understand, is how recursion works. But basically, it's going to do it for you automatically once you come up with your base case and your recursion case. So that's like the beauty of recursion, because it makes it so much easier. It will automatically just do it for you. It's you might have to take some time to think about it and just draw it out, because it takes me a little while to think about it too. But don't spend too much time thinking about it, because recursion always is a little crazy. But besides that, any other questions? Alright, so let's do a different one. Let's do level, order, traversal, binary tree. So, level, order, traversal, binary tree. This is BFS. Remember we just talked about that? Alright, so I'm just going to give you the code for this, so you can kind of see it, and I'm going to explain how it goes, right? So remember, here's our example. Summer 3, we have a queue, right? So we're going to add the queue, process the node, add the children, keep going until the queue goes on. And we have to print, our output has to be a 2D array, and we're printing each thing level by level. So level 1 is 3, level 2 is 920, level 3 is 15.7. Note that's saying we actually care about printing level by level, so we care about what level we're on. So we're going to use a for loop as well inside our algorithm. But this is like our basic template. So here's our template. First of all, what's our edge case on this problem? What if we have nothing, right? Because it says over here, a root is an optional tree node on the top of the code. So base case, right? Edge case, which is different from a base case. An edge case is something that might happen, but it's not always going to happen. So in this case, our edge case is if not root, return just an empty list, right? Super easy edge case. All right, next, we're going to use a queue. Queue is equal to, in Python we use a deck, and we're going to add root to it. So this is the code for that. Basically, we're going to have a queue, and Python's already built in with a double in the queue, which I'll show you a secret about how to do DFS interview. This probably is why Python is the best. You can't do this in Java. All right, next step. While a queue exists, right? While we have something in the queue, we're gonna do this. Current level is equal to empty list, and now we're going to actually process it up level. So we're going to say for doesn't really matter in range of length of queue. So by doing this, we're guaranteeing that whatever happens within this loop is only for the current level. So we're going to just say current is equal to queue.top left, right? And then we're going to say current level dot append current value, and then we're going to say queue dot append current dot left if current dot left. Actually, I'll show you both ways. So if current dot left, we want to append it. If current dot right, queue dot append current dot right. So once we're out of the for loop, we process that level, and we're going to say, we're going to say, what's it called, results, append current level. And then if we just go here, we return results. Let me just double check this, right? Alright. So I run this, beautiful, it's done. So let me kind of zoom out a bit so you can kind of see the full code. Okay, here's the full code. So to kind of reiterate what we did, right? We have like a big list for results. Edge case, if there's nothing there, we just return then the list, or else we have our cube, which starts with the root. Because remember, we can't add a root if it doesn't exist, so we don't have this part, so give us an error for some edge cases. So while the cube exists, we have a current level, and then we have a for loop that will just say, hey, let's make sure that we do all of this stuff in that specific level, because after this for loop is done, we're going to add the current level to the results, and then we'll be to the next level. Alright? And then at the end, we return results. And remember, it's basically the same, right? Get the current node, process it, add children. And now let me show you a easier way, a quicker way of doing this, because Python has better ways of doing things. So this error if current left, and you have an extra space, you do this. You erase it and say if current left, else none. And then over here, you can just say if current right, else none. And that's the same exact thing. Oops, I was expecting indent. Yeah, because I'm going to indent this over here. And just save a couple lines of code. And it's also accepted. So that's just another way of doing it in Python, which I think is a little bit cleaner. Because it just removes a couple extra lines. So yeah, that's breadth first search. Any questions with breadth first search? This is like your template, so make sure you memorize this. Take a picture. What's your question?
How do you use deck?
Deck is a double-ended queue. So that's Python, or you can think of it like a double linked list, and you can think of it this way. With a array, when you pop from the left of the array, or take the 0th index of an array, you have to literally move everything forward one step, and you have to copy everything over. So to remove or to pop from the left of an array is an O of n time complexity operation. If you have a double linked list with a head and a tail, removing the head is O of 1, removing the tail is O of 1. So that's why you use it, because you're able to remove the head and the tail, or aka the front and the back, both in one operation. So you can actually use a double-ended queue as a queue by popping left, or you can treat it as a stack by just popping. So actually, by another fun fact, I just removed the left and the pop left, and now we're using depth first search. So this is depth first search now, because we just popped from the right rather than the left. Just a fun fact. You always have to move these 4 letters to make it DFS, and you can't do that in other languages. So when you're doing graphs and stuff like that, this is really helpful. All right. So any more questions on breadth first search? This is again your template. This is basically just memorize this and just copy and paste it in your brain for every question you probably get the answer right. I'll leave this up because I see some people typing. Alright, moving on. Let's go to LeetCode. Let's look at some more problems. See what else we can do. Let's see. Maximum depth of binary tree. Let's look at that one. Alright, given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest root node. So basically we're saying, what's the maximum farthest you can go steps? So for that, right, step 1, step 2, step 3. Step 1, step 2, step 3. Step 1, step 2. What's the greatest number? 3. Therefore, 3 is our answer. If you look at my solution, we're not going to come up with it because this is basically the same thing. I used breadth first search because I was thinking, we're talking about depth, right? So I think that levels by level means that once we stop doing levels, we're just done. So here's what I wrote. Basically, I was like, all right, well, base case, if not root, we return 0, right? There's nothing there. We're also going to have our cube. Well, cube, we're going to do a for loop, right? Current top left, append children, depth plus 1, return depth. It's like a couple lines of code. Basically, we're saying we're going to keep going through our queue and just doing but first search. We don't care about the nodes, so we're not processing them in any way. We're just literally just searching. We're not even like saving the node. We're just literally going through it and just counting how far we go. Our greatest depth is going to be the last one that we hit. Alright? And then our type complexity for this is going to be O of n, because we're searching all n nodes. Our space complexity is O of n, because we're adding at most all n nodes to our queue. So therefore, it's both O of n for both answers. Can we do this with DFS? Is it possible? Does anyone know? Is it possible with DFS, depth first search? The answer is yes. How can we do this with depth first search? We will level by level depth first search. So how can we do it depth first search? Well, think of it this way, right? Let's just go left. We find our longest path is 2. Okay, let's go right. Our longest path is 3. Go left from here. Our longest path is 3. So depth first search works as well. How will we do that? Actually, let's find out. Let's try it. So this is breadth first search. I actually haven't done depth first search. We're going to do this together. So let's try this. Depth is equal to 0. Let's say DFS, taking their root, depth, current depth. Let's say our max depth is equal to 0. Let's say if not root, what do we do? Return. Okay, let's think. Alright, well, let's just say if it is a root, then we are 1 deeper. So then depth plus equals 1. Current depth. And let's say max depth is equal to the maximum of max depth and current depth. So we're just going to keep comparing it every single time. And then we're going to say DFS root dot left. What's going to be added? So add current depth. DFS root dot right, current depth. And then we're going to go here and see run it DFS root and then 0. Return max depth. Let me see if this works. I'm just going to line it up. Net access max depth was not associated with value, but I thought I did it. Try self that max depth. It works. It was accepted. Cool. All right. So I totally just winged this in 5 seconds, but this is a DFS solution for this question. So as you can tell, let me kind of explain what I just did. I created a global variable called max depth, and I set it to 0. And I just did the DFS function, basically where it takes in a root and a current depth. Base case, if there's no root, you return, and then we're going to process it by just adding 1 more current depth. So we're going as far as we can. And then we're just saying, all right, let's compare. Is our max depth less than the current depth? If it is, update max depth. And then from there, just DFS left, DFS right, starting from 0, call that function, and return the max depth. And that's the whole answer. Right? So we were able to solve this with DFS, and we were able to solve this with DFS. So that's like my point, right? The goal is for you to solve these problems in as many different ways as you can. Because lots of these tree problems, you can solve them with both DFS and DFS. So I recommend you do both, because you get really good practice with that. Because you never know, like, for one of my tree problems at Google, when I had my second screening, they gave me a problem which was post-order traversal, and then they changed it to straight. So I had to change my algorithm, and I had to use breadth-first search afterwards. So I had to rewrite the algorithm and use breadth-first search to solve my answer. So it's good to know both algorithms and practice them both. You don't know which ones you might get in a coding interview. But DFS is usually a lot easier. But I actually think in this case, DFS might be a little bit shorter than DFS, but just barely by like a line or two code. All right, any questions on this problem? All right, I'll show you one more problem. Let's see what else. Lowest common ancestor of a binary search tree. This looks scary. And I'm not gonna do this one, it's gonna take too long. Let's see. Let's do same tree. Alright, here's another example of a tree, and you're going to just keep seeing that this is basically the same thing. Trees are really easy. Once you understand DFS and DFS, these problems are basically just like, how can I, you can just go look at this question and think, alright, how can I implement BFS or DFS in this problem? And that's basically the entire solution for tree problems. So given the root of two binary trees, P and Q, write a function to check if they're the same or not. So that means that basically this 1, 2, 3, 1, 2, 3 are exactly the same because they're structurally the same. Left of 1 is 2, right? And right of 1 is 3, right? They're the same tree. Second case, over here, left of 1 is 2, right of 1 is null. But here, left of 1 is null, and right of 1 is true. Is 2. So this will return false. These are not the same tree, even though they're both 1 and 2, because they have different sizes that they're facing. Right? So in this case, I can just give you the solution. You're just checking, right? What are your base cases? We're saying, all right, if there's no left or right, so basically you're both null, then return true. Our false cases are if, say, we have 1 here, but then 1 not here, right? If this doesn't exist, but this doesn't exist, that means it's not the same tree. Likewise, if this exists and then this exists, but they're different values, it's also not the same tree. So those are our 3 cases again. Base case, there's nothing there for either one, so they both don't exist. Therefore, they're the same. They're both null. They're both end at the same distance. So what that's saying is like if you go 1, then here, then 2, and then we've gone left, and left is null, and then here left is also null. That means they're both leaf nodes, and they both have no left. That's good. We go here left, and then right. Right? If there's no right, and there's no right here, that means they're both similar. And then we're also checking are they the same value? Yes, they are. So they're both 2. Right? So therefore, these are the same 2s. And then we're going to keep doing it with 3. These are the same 3s. And then likewise, we go 1, and we find that this is also 1, and they both have each other recursively, and they're both 1s. Therefore, it's the same tree. So those are our 3 cases here. If not P and not Q, we're given 2 trees, P and Q. If not P and not Q, return true. If not P or not Q, therefore one of them exists, return false. If P value is not equal to P value, also return false because they have the same value. And then we're going to do recursive, right? We're going to return the exact function, and we're going left for both and right for both. So we're saying this is a Boolean. We're saying return instead of the same tree for both. So if this is P and this is Q, we're saying are these the same tree starting from here? And are these the same tree starting from here? So is this the same tree starting from left and the right? Because remember, and both have to be true for it to also be a true answer. So if one of those 2 is not true, it'll return false. Right? Any questions on this problem? This is just like recursion in search at this point again. It's like sort of like a tangential DFS question right there. And we're just recursively going there. Alright. Any questions at all? Alright, let's go to a couple more just to show you some really important ones. I think this is in the LeetCode all. Check here. Here. Insert into a binary search tree. This is a really important one. Alright, this is a really important question. You should probably have learned this in 220, but we'll go over it again. Right? In a binary search tree, the property is like what are the properties of a binary search tree? Can someone tell me actually? What are the specific properties? Left is what? Left is less than the current node, and right is greater than the current node. And this must be true for all lefts and all rights. So if you're given this binary tree, 4, 2, 7, 1, 3, we want to add 5. Where would 5 belong? Well, let's look at it. 4 is 5 greater or less than 4? It's greater than 4. So we're going to put it on the right subtree. Alright, now we're at 7. Is 5 greater or less than 7? It's less than 7. We're going to put in left subtree. Left subtree doesn't exist. It's null. Therefore, we have a spot for it. Does that make sense? Alright, another one over here. The left subtree could be making 5 the new head. But that's a more advanced algorithm to balance the binary tree, because 5 would also be valid. But in that case, we don't have to think about that answer. We're in the first version. That's pretty easy. Alright? The base case is if we reach a null pointer, So we were over here, right? And we said, okay, blah blah blah, we found it here. Okay, here's null, and this is valid. We're gonna add the new node here. So that's the first line of code, saying if not root, return tree node of that new value. So at that point, we're adding it there. All right. And also, if the value is greater than the root that value, then we're going to do it to the right. So the root that right is equal to insert binary tree from there. So we're going to recursively do that basically. Or else it's going to be on the left side. So we're going to insert into binary search tree to the left side. And then we're going to return the root just to return the new tree. Does that make sense? So again, recursion is literally the same thing over and over again. There's nothing too crazy about that. But this is a really core algorithm. You should know how to insert into a binary search tree. But this might actually come up in your 313 exams, actually. Should come up in your 313 exams. Yeah, take a picture if you need to, or else I'll move on to one more binary search tree problem. And then I'll just quickly talk about n-area tree, and that's basically it. So, delete node from a binary search tree is another one you should know. That's just saying, okay, delete a node. So we want to delete 3. We have to delete 3, make 4 the new left, and go from there. All you have to know for that is basically you have to delete it, and like this you can solve on your own, but I'll just kind of tell you, right? You have to delete it with the next equal successor. So basically, what you do is I like to do like the lowest number on the right side of the tree. So if I want to delete 3. The lowest number on the right side of the tree becomes a new current node, so 4 becomes 3, and 3 is removed, and therefore it's a valid tree. If you want to remove 5, you can do 6 would be a valid node for that instead. Usually it's going to be the lowest node on the right side. Or you can actually do the largest node on the left side. But again, just watch that and maybe do this on your own. But as you can tell, like here are a lot of problems on trees, and they're all very much the same thing. You just have to kind of figure out how can I traverse this tree using depth first search or breadth first search, and then how can I solve the problem using those 2 algorithms? Because they're going to be just variations of that core algorithm overall. So I would say trees are actually really easy in that regard. And if you could do trees, graphs is like your next step. And we're actually going to, next session will be graphs. So we're going to talk about adjacency lists, matrices, and all that fun stuff as well, because that's actually my favorite thing. Graphs are really fun. Besides that, any questions at all about what we talked about?
For 313, are they going to specify a language or is it any language?
It depends on the professor. But if you're doing LeetCode, like I said last week, do it in Python, learn Python. It's worth it because it's so much easier. Unless you want to suffer, then don't do Python. But for example, I'm learning like Swift right now. So like I think I actually did this one in Swift. Let me see. That's Kotlin. I didn't do it once, I guess. But I tried doing these stuff in Swift and I wanted to like just poke my eyes out. It's not that fun. Python is so much easier for LeetCode, and since you only have 20-30 minutes in an interview to solve problems, you want to make sure that you use the right tool for the job. Python will give you the answer faster, and then you'll solve the answer faster, and therefore you might get the job over someone who does this in the next seat, because they're going to be busy having segmentation faults the whole time. So do the right tool for the job. All right, one last thing before like we stop on just trees. It's just really quickly just talk about the other type of tree that you might get. It's called n-area trees. So does anyone know what an n-area tree is? If we have a binary tree, which means 2, what is n-area? You can have n amount of children, exactly. So an n-area tree is just a tree that may have here's an n-area tree. See, 4 children, this one has 2 children, right? That's an n-area tree. In this case, it wouldn't be left and right, just to give you a kind of a heads up. This would just be like, be self, not children. And this would usually be a list of children. Yep. And it would have all the children in there. So it would be a list of nodes. That's the only difference. And in this case, actually, like, you know how we talked about like take us to the left or whatever? This would just be for child in whatever children. EFS child. Likewise, for child and children, add child to our cube if we're doing vector search. And that's like the only thing you also want to know is that n-area tree is actually easier because you can just use a for loop. And actually, a graph is basically an n-area tree, just that it doesn't have certain things. Oh yeah, another important pop quiz. This is just like tree stuff. How many vertices are there compared to the amount of edges in the tree? So say we're given a tree here, here. How many vertices do we have? 3. Vertices is like the actual nodes. How many edges or lines connections do we have? 2. So we have 3 vertices, 2 edges. What can we generalize? If we had, it would be n minus 1 edges. That's something you want to remember. For every vertex, for every tree, the most important thing is that there are n minus 1 edges for the amount of nodes that you have in there. They're going to ask you questions like, oh, is this a graph a valid tree? Well, does the graph have n minus 1 edges? If it does, it could be a valid tree, right? That's an important thing you want to know. The amount of edges, n minus 1. 2 edges for 3 vertices, right? Goes on from that. What else do you need to know? N-area trees I talked about. Binary trees, right? We have ternary trees, those are just different versions of n-area trees. But that's basically it. That's trees. Like, I can't really tell you more about trees. Like, they're actually a lot simpler than you think of. It's basically the entirety of tree algorithms. Depth of search, breadth of search, and there's like 100 questions that you can do on trees. So for homework, I recommend you just go to LeetCode.io and then you can do these in like 5 minutes because it's literally just typing out BFS basically. It takes like the whole time. And just go through all those tree problems and just, if you can do the LeetCode 150 tree problems, those are enough for you to understand. If you can do the hard ones, I'm not sharing the screen, but if you can do the hard ones, then you're basically a hardcore gamer at that point. So good for you. I haven't done any hard ones. But yeah, just go to LeetCode.io, do some tree problems, and just do them for a week, and you should be good enough to solve them. Once you feel good on trees, you can move on to graphs, which are really fun actually. You know, I find them to be like the most interesting problems on LeetCode because they come up with some really cool questions. Like as a little teaser, something we're gonna do next time is gonna be rotting oranges, which is really fun. It's just like basically for like you're given a matrix, right, a grid, and some oranges are rotten, and each step that you take, the surrounding oranges become rotten too. And you have to find the amount of minimum steps that it takes for there to be no more fresh oranges. So you start with this orange, this explodes, and now you have a fully rotten grid. So you have to find the minimum amount of steps. So it's actually a really fun problem. There are lots of really cool problems on LeetCode. So we're going to do that next weekend just as a little teaser. I did it with BFS. And yes, there's like 4 lines of code for these problems, but it's all boilerplate, so we'll talk about that later. It's really not that bad. All right. Any last questions?
Scroll back up.
Sure.
No, all the way up. Your tree. Oh, I see your tree.
Oh, like my pictures?
Oh, your
This?
tree list in LeetCode.
Oh, yeah. You can just go to LeetCode.io. If you click on LeetCode 150, oh, here you go.
Thanks.
You're welcome. All right. That's basically it for me. Do you get any last supporting works? Next week we're gonna do. Oh yeah, next week or sometime soon. I don't know. Whenever you want to do it, we'll do some graphs. And those are gonna be a little bit harder. Most graph problems are medium difficulty on LeetCode, and you definitely need to be good at those because when I interviewed at Google, they gave me for my on-site interviews, I had one try problem, which is like a super niche like graph. I had one adjacent to this problem. I had one adjacent to this problem that had to do with trees as well. And then I also had a matrix problem. So they were literally all graphs. I didn't get a single array question, unless you count the matrix as an array. So that's what you want to make sure you know, graphs. But if you know how to do BFS and BFS on tree, you basically know how to do it on a graph too. Okay. See you guys.
Before you go, we have some
Oh, yeah.
snacks here for you to enjoy.
Also,
and
one last thing here before you go, let me just could you please fill out the forms that we need to do. Please just quickly before you leave, scan this to give us some feedback.
we need you to complete the
We need
feedback
to- yeah.
form so he can continue.
If we don't
This
get
workshop
feedback,
series.
we won't get to do these things. So make sure you get feedback. No, actually no. I got rejected from the team I applied to like a week ago. Like 2 hours ago. But I'm like crossing my fingers to get a New York team. I'm hoping.
So we don't have to fly to
Yeah, I don't want to move to California, dude. They asked me if I could do Cali because that's like where all the jobs are. I'm like, I don't want to. But like, if I really have to, I'll